Chapter 4, Motion in 2 dimensions. So now we look at motion in 2 dimensions. So we'll start off with looking back at 1 dimension and then looking at 2 dimensions. So the first thing we saw was position. And in 1 dimension, the position was x, and in 2 dimensions, it would be a vector r. So if this is our xy coordinate system, we have a point here. This would be our vector r. And we have a point somewhere here, let's say over here. This vector would be the vector r, and it would have 2 components, the x and the y components. So r can be written as xi plus yj. So that would be the position of any point on the 2-dimensional plane, and if it is 3-dimensional, you would just add the zk. But in this course, we will not consider the 3rd dimension. Now the next thing we saw was displacement. So in 1D, displacement was a delta x, which was x final minus x initial. And in 2 dimensions, we would see that if this is the x and y direction, and if we have an object initially at r initial, and then it goes to some other point here, let's say it goes here, r final. So this will be, from here to here, would be the delta r. So it goes from r initial to r final, and the displacement would be delta r, which would be r final minus r initial. That's just like x final minus x initial. We have r final minus r initial. And r final would be x final I plus y final j minus x initial I plus y initial j, and that we can write as x final minus x initial I. Note that this I is initial and this is the unit vector I, and plus y final minus y initial j, which would be a delta x I and a delta y j. So in this vector delta r, we can break it up into 2 parts. This would be the delta x I, and this would be the delta y j. So our delta r, or the displacement, is delta xi plus delta yj. Now the next thing is velocity. So in 1 dimension, the velocity was simply dx over dt, and in 2 dimensions, it will be dr over dt, which is d over dt xi plus yj, which would be, let's say, dx over dt I, dy over dt j. And because the velocity vector is a vxi and a vyj, then we can see that this is dx over dt is vx and dy over dt is vy. And if we were to draw on the xy plane the velocity vector, let's say the particle is here and at this instant is going in this direction, so then it will have 2 components, a vxi and a vyj. So the velocity would have two components, and we can find them using this equation. Now we look at acceleration. So in 1D, acceleration was dv by dt, and in 2 dimensions, the acceleration would be simply the same thing, but now v is in 2 dimensions, so it's going to be vxi plus vyj, which will be dvx over dti and dvy over dtj. And the first term would become ax, and the second term would become ayj, so that would become the acceleration. So the acceleration has two components, the x component and the y component. Now a little bit more on acceleration. So if you have an object, like suppose you're in a car and you're going on a highway which is turning. So you're going in a car like this, and at this point you're going in this direction. That would be the velocity vector here. Now this vector must be a straight line, okay? We don't say you're going like that, okay? You may be curving, but the velocity vector is not like that. It's always a straight line arrow. It has to be a straight line. So you're going in this direction. And when you're here, you're going in this direction. So you're always going in the forward direction, and the forward direction is changing. So if this is v1 and this is v2, then v2 is not equal to v1 even if your speed is the same. Because a vector has a magnitude and direction, your magnitude may be the same, but your direction has changed. Okay, v2 is like that. So the magnitude may be the same, but the direction has changed, and therefore it's not the same vector, which means that dv over dt is not 0. So you would have an acceleration if either the magnitude of the velocity changes, and it could also be the same, the direction changes. So either the magnitude or the direction change would be an acceleration. So even though your car is going at a constant speed, but because it's turning, you have an acceleration. We call that the centripetal acceleration, which we will see in the next topic. Now, based on this, we will now look at the equations of motion in 2 dimensions. So again, we will look at the one-dimensional equation, which was Vf equals Vi plus At. Because this was purely in the x direction, this would be in the x or in the y. In 2 dimensions, we can write it as a vector, Vf equals Vi plus At, and the vector V final would be Vx final I plus Vy final j. Okay, so the V is Vx and Vy, Vxi, Vyj, and they're both finals. And these are, the next ones are both initials. So Vx initial I and V initial j. Okay, this I means initial, and that's the direction vector. So that's the V initial. Plus A would be AXI and AYJ. And we don't have AX initial or final because A is constant. Okay, so we don't have the initial and final. A is constant. Okay, now this equation can be broken up into two parts, and we can write it as Vx final, just collect the I terms, equals Vx initial plus Ax, this one, times t. And now we collect the y terms, would be Vy final equals Vy initial plus Ayt. So now we have two equations, say A and B, and these are the equations of motion, one in the x direction, this one in the y direction, and they're coupled together with time. So if an object has Ax equals 0, or it has any value of Ax, it will not affect the y component of velocity. Okay, the y component of velocity will depend only on the initial value and Ay. Similarly, Ax will only influence the x component of velocity. So if Ax is 0, then this whole term will become 0, and the x component will not change. But the important thing is the x component of acceleration does not affect the y component of velocity. So these are two sort of independent equations, but they're coupled together with the time. So the time is the thing that's common to both equations. Now with this, we'll write the other equations, and we'll just go and write them out. So we'll write them out, all three of them. So we have x final equals x initial plus Vit plus half At square. This will become x and x. So this will become the x component equation, and y final equals y initial plus Viyt plus half Ayt square. And then we had the equation that we just took here, Vx final equals Vx initial plus Axt, and Vy final equals Vy initial plus Ayt. Note that these are not vector equations because we are not writing any i's and j's, but we are only taking the magnitudes of the terms. And then the third equation would be V final x square equals V initial x square plus 2ax delta x, and V final y square equals V initial y square plus 2a in the y direction delta y. So we had three equations in one dimension, and now we have three more equations in the second dimension, and we can have three more similar equations if we have the third direction. Now, well, I've written this as xi and ix, so well, it should have been the same, but it's all x component initial or initial in the x component. They're really the same thing. Now we will use these equations to solve some examples.